And we're back. All right, today we're going to talk about two things. Gas stoichiometry, where we're converting to some mass or moles of product from a certain amount of volume. And how we do that is if we are under standard conditions, this is called STP, which is standard temperature and pressure, which we'll always refer to as STP. And that standard temperature is 0 degrees Celsius, or 273 Kelvin, and 1 atmosphere, or 760 torr. But anytime you'll see it used in the ideal gas equation, if you do that, you will get a volume of gas of 22.42 liters, or normally, for our sake, we will use the value of 22.4 liters. So at 0 degrees Celsius and 1 atmosphere, you can assume the molar volume of gas is 22.4 liters. So 1 mole of any gas, whether it's oxygen, nitrogen, helium, of that gas is equal to 22.4 liters. And this has to be at STP. If it is not at STP, you have to use the ideal gas law, because 1 mole will not be equivalent to 22.4 liters. So, for the following problem, it says it's at STP, so that's how we know that we can use the molar volume. So we know we have a sample of oxygen gas that has a volume of 2.50 liters. And we want to know how many grams of O2 are present. So that means we cannot convert directly from liters to grams unless we know the density. We know, since it's at STP, we have to first convert to the number of moles. So we use that molar volume, since it says at STP, we know 22.4 liters of oxygen is equal to 1 mole. And then, finally, moles to grams, we multiply the molar mass by the molar mass of O2, so 2 times the mass of oxygen, so 32 grams for every 1 mole. And when you do that, you get a mass of 3.57 grams of oxygen. Okay, so you should be able to not only convert from liters to grams like you just did, you should also be able to do the reverse, convert grams to liters, when a sample of gas is at STP. Okay, so that's a derivation of the ideal gas law. Another derivation of the ideal gas law is figuring out the molar mass of a particular gas. And we get this equation from the fact that moles in the ideal gas law, we know to convert from grams to moles, we have to divide by molar mass. So the grams of that gas divided by the molar mass, which we will abbreviate mm. So that's how we get the moles of a substance. So we get mass over the molar mass of that particular gas. And if we so we're going to substitute this into the ideal gas law. So we know, for solving for pressure, the ideal gas law is nRT over V. But if we sub this in for number of moles, we get mRT over the molar mass times the volume. And if you notice here, we have on top here mass, on the bottom here volume. So mass over volume that is equal to density. So we can rewrite this equation in terms of density, dRT, over molar mass. So then we can rearrange this equation to solve for either molar mass, which we did up here, that's dRT over the pressure. And keep in mind, still, since we're using the universal gas constant, pressure has to be in atmospheres, and this density will be in grams per liters in order to cancel out this unit. And this unit makes sense because for gases, they are much less dense than liquids, which have their densities in grams per milliliter, or solids, which have their densities in terms of grams per centimeters cubed. So we can solve this in terms of molar mass. So you should be able to plug in those values, get your value for molar mass, and then you should be able to identify whatever particular gas it is, whether it's a noble gas or if it's one of your diatomic compounds. You should, from that, be able to determine the molar mass. And you should be able to rearrange this if you're trying to get the density of a known gas. If you rearrange this for density, it's the molar mass times pressure over RT. Okay, so you can use that in order to solve the following problem. So what is the density of F2 at STP? So that's fluorine gas, and remember, be careful, make sure you're using the molar mass of F2. So we're trying to solve for the density, D, and from the rearranged equation we just said molar mass times pressure over RT is equivalent to density. So first off, the molar mass of F2, the molar mass of F is 19, so times 2, that's 38 grams per mole. The pressure given to us, it's standard temperature and pressure, so our standard pressure is 1 atmosphere. We're still using the same value of R. And then same thing, standard temperature and pressure. So that standard temperature is 0 degrees or 273 Kelvin. And then finally, when we get this density, we get a density of 1.70. And make sure your units of density are correct. They are grams over liters. Okay, so you should be able to use this rearranged or derivative of the ideal gas law for either calculating the molar mass or finding the density of a known gas. Okay, so far we've talked just about individual gases, but normally gases are always in a mixture. Because anytime any two gases are in the same place, they will automatically form a mixture. And when you have a mixture of two or more gases in a container, Dalton's law always applies. Dalton's law of partial pressures. So the total pressure is the sum. You're just adding up the individual pressures of each gas if they were to exert alone. So let's say we have air. If this is oxygen here, if this is nitrogen here, they combine together. The total pressure is the pressure of the nitrogen individually plus the pressure of the oxygen individually as well. Right. And you can calculate each of these partial pressures. You can calculate them using any of the gas laws, whether it's Boyle's law, or you can also do it using the ideal gas law. And we're going to see for the following problems you can calculate or solve these problems two different ways, either using Boyle's law or the ideal gas law. So the two things I want to stress: this pressure exerted is not affected by the identity, and the forces, the intermolecular forces between the gas molecules, must not be important. We're assuming these gas molecules are acting ideally, not like they actually do, like the real gases, where they actually take up space and they are attracted to each other. We're going to cover that later in the unit. Okay, so let's say at first, right now, we do not have a mixture of gases. This valve is closed. Okay, but we want to know, after that valve is opened, what is the pressure of the helium gas? So there's two ways to solve this. We can either, one, use Boyle's law, or two, use the ideal gas law. Because it does say the following apparatus containing helium in both sides is at 45 degrees Celsius. That is constant. So if we're using Boyle's law, we can just ignore that and use Boyle's law. So we know for the left side of that, the left bulb, we're going to use Boyle's law. So the initial pressure and volume, the initial pressure was just 2 atmospheres, the initial volume was 9. And we're trying to solve for the pressure at the end, P2, of this part, of the left part. And then we have to think about V2. Okay, what's the volume, total volume, at the end? And we're assuming that this valve doesn't add any volume. So that means the volume at the end is just simply additive, 9 plus 3. So that means the final volume is just 12 liters. Okay, so that means the final pressure of the left side here, is 1.50 atmospheres. Now we can do the same exact thing for the right side. We're using Boyle's law, and its initial pressure was 3 atmospheres. Its initial volume was also 3. We're trying to solve for P2. And now the final volume is still the same. It's still the total additive volume, 9 plus 3. So V2, still for this side, is 12 liters. So that means, as a result, for the right side, our final pressure, when we calculate that out, is 0.75 atmospheres. So now we have the partial pressure of each side. Now to get the total pressure, we add these two together. Pressure of the left side plus the pressure of the right side, so 1.5 plus 0.75 atmospheres. That means we get a total pressure of 2.25 atmospheres. Okay, so we could also calculate it using the ideal gas law, since we are given temperature. So what we can do, so we have the temperature, we have the pressure, we have the volume of each side. So that means we can calculate the number of moles. We can get the total number of moles, and from that, get the total pressure. Okay, so what we can do, we can get the number of moles of helium on the left side using the ideal gas law. We're solving for number of moles, so PV over RT. And our initial pressure there is 2 atmospheres. Our initial volume is 9. We use our known value of R. And then for temperature, remember it has to be in Kelvin. So 45 degrees Celsius plus 273 is 318 Kelvin. And when we do all that, we get the number of moles on the left side as 0.690. And we can do the same thing for the right side. Its number of moles. And its pressure is 3, its volume is 3, and still that temperature is still the same, 318 Kelvin. And when we do all that, we get the number of moles of 0.345. So now we have the number of moles on each side, on the left side and the right side. So this is number of moles on the left, number of moles on the right. To get the total number of moles, just simply add them together. So our total number of moles would be 1.035. So now that we have the total number of moles, now we can go back and calculate for the final pressure using the ideal gas law, now that we know the total number of moles. So that means for the total pressure, it's the total number of moles over the times R times T over the total volume. So we just said the total number of moles, 1.035 times R. Our temperature is still the same. Remember, it's still constant. Then the total volume, the combination of both bulbs, once the valve is opened, is 12 liters. And when you calculate all that out, the answer agrees with the previous one, 2.25 atmospheres. So I think normally if something is constant, like temperature is constant in this problem, I think it is easier to just use Boyle's law rather than using the ideal gas law. So for this next one, you can use the same thing. You can use ideal gas law, but since here temperature is constant throughout for both the oxygen and helium gas, you can ignore it, and the only thing that's changing is volume and pressure. Now this one's a little trickier. Last one we were just combining helium gas. Now we're combining oxygen gas with helium gas. Okay, so first for this oxygen gas, we have its initial volume and we have its initial pressure. So we're going to use Boyle's law once again. So we know its initial pressure 1.30, its initial volume 27.4. We're trying to get what's the new partial pressure of oxygen, so P2. And you look, we're taking this volume and this pressure of oxygen gas, combining it with helium gas, and putting it into a new tank with this volume. So that is our new volume. That is our V2. And when we do that, when we solve for P2, you get a resulting pressure of oxygen of 6.13 atmospheres. Okay, now we can do the same thing for helium. Use the ideal gas law. So the initial volume of helium is 8.50, and the initial pressure, 2.00 atmospheres. And same thing, we're solving for the new pressure, the new partial pressure of helium, and it's going into the same exact tank. So this is the new volume. So we're still using 5.81 liters as our V2. And there, when you solve for P2, the new pressure of helium is 2.93 atmospheres. So now that we have the individual pressures, we can calculate the total pressure by adding the partial pressure of the oxygen plus the partial pressure of the helium. So 6.13 plus 2.93, and we get a resulting total pressure of 9.06 atmospheres. Okay, and much like before, since we're using Boyle's law, it doesn't matter if the units of pressure are in atmospheres or torrs or kPa, and same thing for the volume, it could be in liters or milliliters. Those units don't matter as long as they match, since we're not using R. Now, we could have solved this using the ideal gas law. In that case, then the volume has to be in liters and the pressure has to be in atmospheres. And remember, always, this temperature should always be converted to Kelvin if we're using it. So much like the last one, we could have solved this with the ideal gas law, getting the number of moles of each, the moles of helium gas, the moles of oxygen gas, adding them together to get the total moles, and then using the ideal gas law to get the resulting total pressure. All right, that's it for today. See you next time.